the 2021 AP Calculus AB free response question number 1. Here we have a table problem, and number 1 reads, the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Values of f of r for selected values of r are given in the table above. So I'm going to scroll down so you can see parts A through D. Feel free to pause the video at this point and try these four parts of the problem. What we're going to do in the coming slides is look at each one separately. So let's begin with part A. Use the data in the table to estimate f prime of 2.25 using correct units. Interpret the meaning of your answer in the context of this problem. So let's go over the calculation here first. To approximate a derivative from a table, we're going to use the average rate of change of the smallest interval that contains the designated input value. So we have 2.25, which is going to represent the distance from the center of the dish, and that is going to be contained within the interval from 2 to 2.5. So we're going to calculate the average rate of change from 2 to 2.5. So we're going to say f prime of 2.25 is approximately f of 2.5 minus f of 2 over 2.5 minus 2, that being our average rate of change calculation. Now f of 2.5 and f of 2 were given to us in the table. They were 10 and 6 respectively, so we're going to substitute those values in. And when we clean this up, we're going to get 4 over 0.5, which is 8. So we now know that the derivative at 2.25 for f is approximately 8. Now, using correct units, interpret the meaning of your answer in the context of this problem. So the correct units would be milligrams per square centimeter per centimeter. So we can see f is measured in milligrams per square centimeter given in the table, and then the input is measured in centimeters. So the rate of change of f would be, I'll write it down here, milligrams per square centimeter per centimeter. Okay, so that's our units for our derivative. Now, interpreting the meaning of our answer in the context of this problem, we would say something like you would write, so at a distance of 2.25 centimeters from the center of our dish, because that's what our input value is, we would say what is f measuring? The density of bacteria population. So we would say, so at a distance of 2.25 centimeters from the center of the dish, the rate of change of the density of the bacteria population is increasing by 8 milligrams per square centimeter per centimeter. So we're recognizing how f is measured, and we're describing that within the context of, or using that for the description of the context of our problem. So once again, we're going to say at a distance of 2.25 centimeters from the center of the dish, the rate of change, so it's important to include that language because we're showcasing a value for a derivative, of the density of the bacteria population is increasing, and we're saying it's increasing because the derivative value is positive, at 8 milligrams per square centimeter per centimeter. So now let's move on to part B. The total mass in milligrams of bacteria in the petri dish is given by the integral expression 2 pi from 0 to 4 r f of r dr. Approximate the value of 2 pi integral from 0 to 4 r f of r dr using a Riemann sum with 4 subintervals indicated by the data in the table. So a Riemann sum is just a matter of calculating areas of rectangles. So we're going to need a base and a height. We know the base value of our rectangles are going to be defined by the lengths of the subintervals. So when we take a look at this table, we can see the subintervals are not all going to be of equal length. So we want to pay attention to that. We can see that from 0 to 1 and 1 to 2 are both 1, but from 2 to 2.5 is only 1/2, and from 2.5 to 4 is 1.5. So something to note there. And then where does the heights of our rectangles come from? Well, because it's a right Riemann sum, we're going to have to take into account the right output on a specific subinterval. So the right outputs for subinterval 1 would be 2, then 6 would be for subinterval 2, 10 would be for subinterval 3, and 18 would be for subinterval 4. However, it's not just using the output of the function r for the height, but rather we also have to consider it scaled by the value of r itself. So that's the key to this Riemann sum approximation. We can see that the integral involves r times f of r. So in general, when we take a look at an integral and we have, say, f of x dx, we know the dx, we can think of that as the base values of our rectangles that are used to approximate or define the integral as the number of rectangles approaches infinity along the interval. And then f of x represents our height. So if f, or this, I maybe should have used a different letter, so say g. So we can think of g as being defined as r times f of r. Okay, so we're going to have to account for that value of r when computing the height. So let's set this up. So we're going to say 2 pi, the integral from 0 to 4, r f of r dr is approximately, I'm going to say 2 pi. And then inside, okay, so for our first subinterval, we know the base is 1. Okay, so we're going to say 1 times, now our height is going to be r times f of r. And again, the f of r value we use has to be the right output along that first subinterval. So the output is 2, and then the r value is going to be 1. And what r value we're going to be using? We're also going to be using the r value on the right of that subinterval. So it's going to be 2 times 1 to get our height. So we have our base, we have our height for our first rectangle. So we're going to do plus our second rectangle, the base value. So along the second interval, that difference is 1. So maybe I'll put a subscript. So now we're working on rectangle 2. And then the height is going to be r, which again is 2 times 6. That's going to get us our height. Then we're going to say plus. Now base 3 is going to be a half. And then output's going to be r value of 2.5, and then f of r value of 10, right output. So height 3, and then plus. And we're going to have 4 and 18. Okay, so the difference for the base is 1.5 for base of rectangle number 4. And then we're going to have r value of 4, and then times an output at 4 of 18. Now we have a calculator that would allow us to clean this up. And after going to the calculator, we're going to see this all cleans up to 269 pi. So there is our computation for an approximate value of the integral from 0 to 4, r f of r dr, all times 2 pi. So a quick recap before we go on to part C. One thing about this problem we want to pay attention to closely is the fact that this function within the integral is r times f of r. So that r value is going to come into play when calculating the heights for your rectangles on your Riemann sum. So don't fall into the trap of just thinking the heights are only dictated by the output at f, or of f at a specific value of r. And being a right Riemann sum, it's going to be the right endpoint of each subinterval. But you also have to scale that output by the value of r. So one small wrinkle, but enough to throw off your final answer if not considered. So let's move on to part C. Is the approximation found in B an overestimate or underestimate of the total mass of bacteria in the Petri dish? Okay, so when you use a Riemann sum as an approximation for an integral, it will be an overestimate or underestimate depending on, one, if you have a left or right Riemann sum, but also if the function's increasing or decreasing. So if we have a decreasing function, a right Riemann sum would be an underestimate. But if we had a strictly increasing function along the designated interval, then we're going to have an over approximation. So our goal is to determine, well, is this function increasing or decreasing? Now, the function we have to analyze is the function that was within the integral that was used to determine the Riemann sum. Okay, so we want to be careful and not just think again that we're using f as our analysis, or the function for analysis here. So within that integral was r times f of r, right? That was the function used to approximate the Riemann sum. So we want to know, is this increasing or decreasing? Well, how do we determine that? Well, we analyze its derivative. So if we differentiate with respect to r, of r times f of r, this is a product of two functions, so we're going to have to do the product rule. So left d right plus right d left, which is just 1. So this is the function we want to look at. So is this function positive or negative? That will determine whether or not r times f of r is increasing or decreasing. So now, what do we know about these three pieces that compose this derivative? So we have r. Well, let's take a look at the r values in our table. R is always positive, and it measures a distance from the center, so that should make sense. So this is a positive value. F prime of r, so the derivative has to be positive because we are told that we have an increasing function. So a positive times a positive is equal to a positive. So we know that that first piece is positive. And what about f of r? Well, f of r is measuring the density of the bacteria population. So that also makes sense that it's positive values. And we can see that on that interval from 0 to 4 that we used to approximate the derivative, or sorry, to approximate the integral, we see that these are positive outputs as well. So this portion is also positive. So a positive plus a positive is equal to a positive. So because we have a positive derivative, so we can see that this is going to be greater than 0. So we're going to say because r f prime of r plus f of r is greater than 0, the approximation in part B is an overestimate. Now we should probably put some language in our answer as to why this derivative was positive. So I reasoned through that verbally, but worth writing down. So now we know our answer. Because our derivative is greater than 0, we have an increasing function. And because it's increasing along the interval that was used to approximate that integral, we know that that right Riemann sum would be an overestimate. And then let's look at part D. The density of bacteria in the Petri dish from 1 to 4 is modeled by the function g, defined by 2 minus 16 cosine of 1.57 square root of r cubed. For what value of k from 1 to 4 is g of k equal to the average value of g of r on the interval from 1 to 4? Okay, so we have an average value here. So we know average value of a function along the interval from 1 to 4. So we're going to say so this would be our average value. We want to know when this average value equals essentially g of r. And then when that equals g of r, where r is this k value we're looking for, we'll get our answer. Okay. So how are we going to do this? Well, we have a calculator. Okay, so we don't actually want to try to solve this algebraically. So what I would do is we're going to use the graphs of these functions to see where they intersect. So the first thing is on my TI-84, I'm going to restrict the window of x from, so my x min will go from 1, and our x max will go to 4 to make sure we're just only looking at the specified interval. Then what I'm going to do is I'm going to graph in y1. I'm going to graph the function g. So I'm going to say 2 minus 16 cosine 1.57 square root of x cubed. And then in y2, I'm going to graph the average value. So I'm going to say 1 divided by 3, right, because that would be the result of 1 over 4 minus 1. And then I'm going to plug in the integral from 1 to 4 of that function g. So 2 minus 16 cosine 1.57 square root of x cubed dx. Now, when I graph these on my calculator, the image we're going to see is, and we might have to adjust the y window as well. So the y output, what you would see, is very close to 10. So you might want to make your y max, say, 20. So that's what I did. And you're going to get a graph that kind of looks something like this along your interval. In that point of intersection, that's going to be our answer. Okay, so now how do we get that point? We're going to do that intersection calculation on our calculator, and we're going to figure out that this point, which is going to represent our k value, is 2.497. So that is the value of k from 1 to 4, where g of r is equal to its average value along that interval from 1 to 4. And there's your answer. So this was all done on a calculator. Okay? And being the calculator section, totally valid move. And that's all you have to do. So don't try to do this algebraically. Now, it does require you to know how to compute an average value, right? So that involves an integral. And then we have to divide by the length of the interval. And yeah, and we're just going to graph them. A little window manipulation was necessary there. And then we just figure out where those two graphs intersect. So there's our answer for part D. And that is number 1 on the 2021 AP Calculus AB exam.